Okay, let's start. Thanks for joining the makeup session. Today, we would like to conclude lesson 2. So we have a lot of work to do. But before we move on, let's go back to the slide we have seen the day before yesterday. See, in our example, we have assumed the game bandwidth is 100 gigahertz. Okay, but even in steady state, the pulse 25 picosecond corresponds to a bandwidth only 18 gigahertz, which is much narrower compared with the game bandwidth, right? So in theory, we expect that the pulse should be shorter and shorter. Meanwhile, bandwidth is broader and broader until limited by the game bandwidth, right? But according to our calculation, according to our model, it seems that well before that happens, the pulse shortening effect ceases to exist anymore. So the pulse width simply stops at 25 picosecond. Okay? And my question is why? Why the pulses cannot be shortened again and again until limited by the 100 gigahertz bandwidth? That is a natural limit you cannot surpass, of course. But in the active mode locking lasers, as shown in this example, it seems that before the game bandwidth limits your pulse width, something else happens such that the shortening effect is no longer useful. Okay, and why is that? So that is my bonus question. Maybe use this slide. Okay. The blue curve is the intensity modulation contributed transmission curve. And the red one is the steady state pulse. Okay? We also know the pulse shortening effect comes from the modulation, the blue curve. But why the loss modulator cannot keep on shortening the pulse until limited by the game bandwidth? This is a bonus question. Do you get what I mean? 理论上，脉冲的压缩最终一定会被 game bandwidth 所限制，因为你的 game medium 没有办法提供更大的频宽，所以你的频宽被限制，你的脉冲就会被限制。但是似乎在这个作用发生之前，脉冲已经停止被压缩了。Okay, so according to our numbers, steady state bandwidth, steady state pulse bandwidth is only 18 gigahertz, but game bandwidth is 100 gigahertz. So the boundary has not been reached yet, but the pulse can no longer be shortened by the blue curve, the loss modulation curve. But why is that?
你说的 game bandwidth 是有已经考虑过 loss 之后的 game bandwidth。
What is the blue curve only comes from the modulator. It's independent of your game medium. Game bandwidth is provided by your game medium only, independent of your modulator. In our model, we separate them into two different formulas, right? So this is a very interesting question, and it will highlight our motivation that a new technique is needed if you want to generate even shorter pulses. Okay. So I can give you a hint. Just look at the blue curve with respect to the red curve carefully. Okay? We know the pulse shortening effect comes from the curvature of the blue curve with respect to the red curve, right? So your red peak, your pulse peak sees the maximal transmission, but your pulse wings see lower transmission. So you can cut your shoulder such that the pulse width becomes narrower, right? That is the pulse shortening effect in active Molag lasers. But be careful, what happens if your red pulse becomes shorter and shorter? What's the problem? When this pulse is pretty broad, apparently this pulse shortening effect is very effective, very useful. 下面的是吗？ This is time domain, so this is not a longitudinal mode. This is a single pulse in the time domain. Please.
等于是说都已经没有马球在得到，就是没有，因为你是靠那个坡度在马球内得到，可是你 peak 太靠近中间的话，等于说基本上你就是全空的状态。
Perfect. You see, as the red pulse becomes narrower, it sees only a small range of blue curve, which could be relatively flat. If it is truly flat, there is no modulation, there is no shortening effect, right? So initially, the shortening effect is very powerful. So the pulse width decreases fast. But as the pulse gets shorter and shorter, the same modulation curve can no longer shorten the pulse anymore. So well before your gain bandwidth is fully accessed, the pulse width cannot be even narrower. Okay? So there is a room to improve. If you want to create even shorter pulses, you have to replace the blue modulation curve. That is the working principle of passive Molag lasers, as we will discuss in the subsequent sections. Okay, good. So your student ID? Very good. Now, another question is, why is Gaussian? Remember, initially, we already assumed the steady-state pulse shape is Gaussian. But why is Gaussian? Okay, here is a simple explanation. Both the gain spectral function e to the g of omega and the loss modulation function eta of t are approximated by Gaussian functions in our model, right? This is the g of omega, your gain coefficient spectrum. After Tyler series approximation to the second order, you have this. And put big G to the exponent, you got this. And you can see this term represents a Gaussian function, right? For the modulation transmission function, we also use a Gaussian function to approximate. Okay? So both this one and this one are Gaussian functions. And we also know multiplication of two Gaussian functions, Fourier transform of a Gaussian function remain Gaussian. Okay? So it enables a self-consistent solution. What is self-consistent? Remember, in our strategy, we have to force the output pulse the same as the input pulse after one round trip, right? If you can do so, you have self-consistent. And it seems that Gaussian function is a smart choice because no matter what happens, either the cavity effect, gain medium effect, or the modulator effect, the functional remains Gaussian. And if you can maintain the Gaussian function, you can arrive at self-consistent solution. If your functional changes, it's impossible you can have self-consistent solution, right? Okay, so that is the reason why we assume steady-state pole shape is Gaussian, because we need self-consistency. Okay. Okay, let's move on to the second approach to deal with the steady-state active Morelock laser pulse. It's called the couple rate equations approach. There are very similar things we have to deal with. We have to model the co-cavity effect, gain medium effect, intensity modulator effect. Eventually, we will arrive at a system of rate equations. Then, by solving this system of rate equations, we can also get the steady-state solution. But this time, it's very different from the first approach. Okay? Before we do so, let's clarify what are the problems of using the first approach, assuming a Gaussian solution. Okay? That approach provides a self-consistent, stable solution, which is good, but there are two major drawbacks. The first one is it cannot answer whether pulses of other shapes can also be solutions to active Morelock, right? You already find Gaussian is a solution, but there is no guarantee no other solutions are possible, right? So this is the loophole of the first approach. Second, how are the cavity modes phase locked together in the presence of intracavity modulator? Remember, in the end of lesson 1, we discussed how to generate a short pulse. In addition to broad bandwidth, we need to lock the phases of all the frequencies, right? That's why it's called Morelock lasers or Morelocking. But in the first approach, we saw no Morelocking mechanism, right? We simply get a solution, Gaussian solution in steady state. But how the phase locking is achieved, we have no answer. But if you take the second approach, we can answer these questions. So first, the model of co-cavity. Okay? Consider a co-cavity of round trip time, big T, which is path length L over light speed c, and the field loss coefficient small l, as we defined before. Then the electric field of the Q's cavity mode. Q is an integer, which is real part of E sub Q of t, where the complex function E sub Q of t is written in this way. Big E sub Q is a complex number or phasor, right? And times the carrier term e to the j big omega qt. Big omega q is the corresponding angular frequency of the Q's mode. Okay, so what is the angular frequency? Your carrier frequency, omega 0, plus q, which is an integer, times delta omega, mode spacing, right? Mode spacing is 2 pi over big T, as we have known. And here we also assume your carrier frequency happens to be some integral multiple of the same mode spacing, delta omega. Say it's the integer is p. Okay, so p is an integer, Q is also an integer. So that is your angular frequency of the Q's cavity mode. Then what happens after one round trip? The complex field E sub Q of t becomes a new field, which is denoted by EQ prime of t. It's equal to the original field E sub Q of t times the product of two terms. E to the minus L means the cavity loss. Okay? E to the minus j times k sub q times L means the accumulated phase. Okay? But it ends up the second term can be eliminated. Why? Because the product of kq and L is simply some integral multiple of 2 pi. And it's justified here. K sub q means the angular frequency over light speed in vacuum times the path length, big L. And by substituting the definition of omega 0 and the delta omega, you can easily show the phase change, phase shift is some integral multiple, which is p plus q is still an integer, times 2 pi. So if your phase is some integral multiple of 2 pi, that means the number is just 1, right? So the term can be eliminated. So it ends up that output field is simply the input field times e to the minus L. You only see the cavity loss effect. Then we have to consider the interaction between optical pulse and the cavity. Okay? So the blue arrows represent the cold cavity modes. As we have seen in lesson 1, if you have a cold cavity, the permitted oscillation frequencies are a grid of discrete frequency components, equally spaced by delta omega, the mode spacing. Okay? But if you use an intensity modulator in an active Mont-Lac laser and driven by angular frequency omega m, in the future I will justify why the driving frequency is slightly smaller than the mode spacing delta omega, although very close, but it's slightly smaller. Then the steady state electric field must be periodic of period Tm determined by your driving frequency. Okay, so the idea is quite simple. If you drive your cavity with a frequency omega m, in steady state, the field has to be of the same frequency, omega m. It's determined by your modulator anyway, okay? So in that case, your electric field is superposition of different pulse modes, okay? The nth pulse mode has a phasor E sub n and the angular frequency omega n, where omega n is defined as carrier frequency omega 0, the same as before, plus n, which is an integer, times modulation frequency omega n. Okay? So what are the corresponding pulse modes? They are represented by the red arrows. Okay? The central one aligned with the blue one because they are carrier frequency, or n equals 0. But for the neighboring two modes, you can see the red arrows are different with the blue arrows by a small amount of frequency detuning, determined by the difference between modulation frequency omega m and the cold cavity mode spacing delta omega. Okay? And for farther away side modes, the difference the separation is larger and larger, right? So here I just pick up the central 5 modes for illustration, but you can imagine if you have more and more side modes, the red arrows will be away from the blue arrows farther and farther, okay? And we defined a frequency detuning factor, delta, in this way. 1 minus delta omega over omega n, which is a number without unit, okay? So if they are the same, if your driving frequency is exactly the same as mode spacing, delta is 0. 1 minus 1 is 0. There is no detuning. But whenever there is difference, your delta is no longer 0. So this number characterizes how big the frequency difference is, okay, between omega m and the delta omega. Any question? Okay. Then what happens after one round trip? Okay. Your electric field becomes a new one, which is E prime of t. Say the nth mode has a new phasor, En prime. Angular frequency remains omega n. And according to our analysis, after one round trip, you have cavity loss, so you have to multiply e to the minus L. You have phase shift, so you have to multiply with e to the minus jknl, okay? But be careful. This is sort of different from the previous example because now the phase accumulation, kn times L, is no longer some integral multiple of 2 pi. So you cannot simply cancel this term as before. But what is the corresponding product? Okay, you can go through the analysis. Eventually, you can find the phase accumulation is summation of 2 terms. The first one is still some integral multiple of 2 pi, which is unimportant. But you have a multiplication factor, n times omega m times detuning factor delta times your round trip time, big T. Okay? So for that reason, the new electric field, the phasor En prime, is related to the old phasor En by factor, including the contribution from the cavity loss, as well as the residual phase accumulation. Okay? So it's not like the previous case. At that time, there is no second term. You have loss effect only. But in this case, if there is frequency detuning, your driving frequency is different from your cavity mode spacing, this term will not disappear. You have to maintain this term. Okay? Now we can try to write down the corresponding rate equation for the nth post mode. Okay, remember we have two systems of modes. The concavity modes represented by blue arrows and the post modes represented by red arrows. Now we are talking about the post modes, the red arrows. Okay? Here we assume the loss and the frequency detuning are very weak. That means your loss coefficient L is quite small, less than 1. Your frequency detuning factor delta is also very small, much less than 1. Under these conditions, you can approximate your relation to this one. Okay? It's very simple. E to the something, when the exponent is very small, it can be approximated by 1 plus something, right? Which is the well-known Taylor series approximation. So you just copy the exponent to here, you got this approximation. But remember, this is only true when the two assumptions are satisfied. Your loss cannot be big. Your frequency detuning has to be very small, okay? But they are usually true in reality. Then, starting from this relation, we can rewrite it, okay? So En to the right-hand side is moved to the left-hand side. You got En prime minus En, which is the difference between the phasors, okay? Remember, what is En prime? After one round trip, what is the new phasor? En, the old phasor. So their difference means the change of phasor in one round trip, okay? Which is approximated by this one, a minus of loss coefficient plus j, which is square root of minus 1 times n omega m delta t. So this is a complex number, okay? L, real part. N omega m delta t, imaginary part. So this is a complex number times En itself. Then you can divide big T for both sides of equality. So the left-hand side becomes this one, the right-hand side becomes this one. Then we further assume if your phasor, E sub n, only slightly changes in one round trip time, big T, so it means your cavity effect is pretty weak. So your phasor only changes a little bit, okay? Not much. Then the left-hand side is approximated by first-order derivative, right? If big T is pretty small, the difference is pretty small, then the difference quotient can be approximated by first-order derivative, right? So you have En time derivative, and you can move the right-hand side to the left-hand side in this way. The imaginary part is here. The real part is here, where we redefine tau 0 as a time constant, which is equal to round trip time over your loss. Okay? So this is so-called the cavity lifetime. If your loss coefficient L is bigger, your cavity lifetime is shorter. That means the electric field cannot survive in your cavity for long because it's lossy. On the other hand, if your loss coefficient L is small, it means your electric field can survive for a long time. Your cavity lifetime tau 0 should be long. Okay, that's the justification. So we arrive at equation 1, which is a differential equation. For what? For En. What is En? The field phasor of the nth pulse mode. And remember, we are talking about short pulse laser. So we have a lot of pulse modes, not just one. So when n equals 0, 1, 2, 3, 4, you have more and more ordinary differential equations to be coupled together. Okay? But at this time, there is no coupling yet, right? Because En is independent from En plus 1, En minus 1 yet. There is no coupling at this point. But in the future, you will see in our model, these modes are coupled together in the end. Any question?